Greetings to you. Welcome to Physics with Ben. Don't forget to like my videos, subscribe and share to those that need it. In today's video, I would like us to look at the theory behind the potentiometer, the Wheatstone Bridge, the meter bridge. If you recall, I did a video, I ran an experiment on potentiometer, and I promised in that video to give us a theory on potentiometer, and this is the video. So click in the description box below and you will see the link to the video which I did on potentiometer experiments. Don't forget to watch all the series so that you don't miss it out. So, what do we mean by a potentiometer? Let's begin from here. We start with potentiometer. A potentiometer is simply a device to precisely or to accurately measure the e.m.f. or the potential difference in a circuit. It measures the e.m.f. with no error. The potentiometer is also used to compare and to know the unknown e.m.f. in the circuit. It is also used to check or to measure and know the value of the unknown resistance in a circuit. Before we are going to understand or have a grounded knowledge on the theory of potentiometer, kindly recall the factors affecting the resistance of a wire. Right. Factors affecting the electrical resistance of a wire. Basically, there are four factors that affect the resistance of a wire. Number one, we have the length of the wire. The length of the wire. Number two, we have the temperature. We have, let's call it change in temperature. Change in temperature. Change in temperature. Change in temperature. Number three, we have the cross-sectional area. So right, area of the wire. And then number four is the nature of the wire, or let's say the permittivity. The resistivity of the wire. Yes, we call it nature. We call it nature slash resistivity. Nature slash resistivity of the wire. Good. Now, how does the examiners may ask you to list the factors, to list and explain the factors that affect the electrical resistance of a wire, and they'll ask you how does these factors affect the resistance of a wire. Very simple. It is believed that the length of the wire and the resistance of the wire, they are directly related to each other. And so we write that the resistance of a wire is directly proportional to the length. It means that increase in the length of a wire will cause the resistance of the wire to increase. Before I proceed, this is what we call the potentiometer in physics. If you watch the other videos, I use this guide to run an experiment. Kindly click in the description box below to watch that video. This is a potentiometer, simply a device with a length of a wire stretched across a meter rule, meaning 100 cm. This is it. This is where we do the connections, here and here. So what we are saying is that if we are running an experiment in this topic, increase in the length of the wire will cause the resistance to increase. I will explain that shortly. Let's move on. So it means that increase in the length of the wire will cause the resistance to increase. How about the temperature? The temperature is the same thing. The resistance of the wire is directly proportional to the change in temperature, the theta. How about the area? The resistance of the wire is inversely proportional to the cross-sectional area of the wire. How about the resistivity? The resistivity is actually the constant called rho. Now, combining all these proportionalities together, we are going to arrive at one equation. We call it a joint variation or combined variation. So we are free to write that. We are free to write that R is directly proportional to L and inversely proportional to L, and also change in theta, and inversely proportional to A. We are not going to include this because this guy is a constant. So let me just clean this for now. So removing the sign of proportionality here, we can write that R is equals to resistivity rho L change in temperature all over A. So what is the meaning of this equation? Very simple. It means that this guy is a constant called resistivity or nature of the wire. While this is the length, it means that increase in the length of the wire will cause the resistance to increase. And increase in temperature of the wire will also cause the resistance to increase. Now mind you, this only happens in conductors. If you are treating basic electronics, that is semiconductors. In semiconductors, for conductors, the resistance of the wire is directly proportional to change in temperature. But then, for semiconductors, the resistance of the wire is inversely proportional to change. Is inversely proportional to change in temperature. It means that for semiconductors, when the temperature is increasing, the resistance will decrease. I will explain this properly. Let me just finish this one now. I will explain it one by one. What I'm saying is this. Between this and this guy, this resistance is a dependent variable. While the length, the temperature, and the area, they are independent variables. That is, the value of the resistance is dependent upon the value of the length of the wire, the value of the temperature, and then the value of the area. That is it. Do you get? So, what I'm trying to say here is that if you make this guy sort of the formula, you're going to arrive at rho L, the theta, is equals to rho RA. You divide both sides by rho the theta by L the theta by L the theta. You are going to have the resistivity is given as rho RA all over L the theta. Now in so many textbooks, you only see resistivity is given as R A all over what? R A all over length. So dimensionally, resistivity is given as R is given in ohm, area in meters square, and length in meters. So why don't you cancel this? So the unit for resistivity is ohm meter. So this is the equation that controls the resistivity of the wire. So what I'm trying to say is that for a now this resistivity, the resistivity of the wire is related with the conductivity of the wire with this equation. It means that for a conductor, as the temperature is increasing, the resistance will increase, and then that will also cause the conductivity to decrease. So it means that increase in conductivity will cause decrease in resistivity and vice versa. How about a semiconductor? For a semiconductor, let's say R semiconductor, RSC semiconductor. For this is what you have: change 1 over change in temperature. For a semiconductor, increase in temperature will cause the resistance to decrease. Now, for a semiconductor, what you have, the resistance of the semiconductor, increase in temperature will cause the resistivity of the semiconductor to decrease, and this will cause the conductivity to increase. So for a semiconductor, the conductivity of a semiconductor is directly proportional to what? To change in temperature. So increase in temperature will cause the resistance of the semiconductor to decrease, and it will cause the conductivity to increase. That is that for that. So if I clean this, I'm going to introduce Ohm's law into this equation. So take notes. So right now we can call this equation number 1, equation star. And if you come down here, I told you that in textbook is what you have. You can call this equation number 2. And again, I said that the resistivity is related with 1 all over this with the conductivity of the wire. And this is the same thing as equation number 3. Now, if we introduce Ohm's law here, we know that V is equal to IR. If you write that correctly, what you have? From V is equal to IR, we know that the resistivity is given as R. Let's rewrite it this way. Let's write R is equals to rho L all over A. We know that V, you can call this equation number 4. We know that V is equals to IR. And if we make V R instead of the formula, we know that our R is equals to V all over I. So we can call this equation number 5. So this implies that you put the whole of this to this place. So this implies that V all over I is equal to rho L all over A. What's the meaning of this equation? So this also implies that V all over I is this L all over A. It means that increase in the length of the wire will also cause the voltage to increase. Does it make sense? Increase in the length of the wire will also cause what? The current to decrease. So there are moments where you have to run equations, to run experiment using this particular equation. So this is that for that. The examiners may ask you to list the factors, to list the advantages of a potentiometer over advantages of potentiometer over the method of measuring e.m.f. Number 1, the potentiometer measures e.m.f. precisely with no error, accurately, while the voltmeter cannot do that. The reason that the voltmeter has a pointer, and you may have what is called 0 error in the pointer. We also have the potentiometer can measure the e.m.f. of a cell when the current is not passed through it. But for you to find the e.m.f. of a cell using potentiometer, the cell has to be connected. That is that for that. So the connection diagram for For this, I would like to explain this quickly. For this guy is simply something like this. So all these equations are peculiar to the potentiometer. Please take note of all these equations. So these are the theory involved. So if I draw something like this, length of a wire, let's call this A, B, and another equation, how a potentiometer can be used to measure the e.m.f. of a cell. This is the diagram I want to use it to explain that I'm connected to a key back here, and then a galvanometer G, and then a jockey touch at any point here. So this is your plus, this is negative, current will flow in this direction, come down here, plus current will, in this way, current will flow this way, and then back in here, down here again. So what we're trying to say is this: call this your E1, call this your E2, and then where these guys touch, this is demarcation. How does it use? The potentiometer is used to measure the e.m.f. of the cell by this particular arrangement. The jockey is tapped at this line AB until you get to a point where you have zero deflection on the galvanometer. The galvanometer has zero this side at the middle, then can go clockwise and also anti-clockwise. So you keep shifting this until you get to a point where this guy is pointing at just zero. At that point, we call it the null or the balance point. The null or the balance point. At that point, the length from here to this point, we call it the length from here to this point, we call it, this is L1. And the length from this point to this point, we call it L2. Yes, we call it L2. We call it L2. So the equation used for that is simply this E1 all over E2 is equals to L1 all over L2. With this, we are able to make since this is here, if it is pointing at 50, if it is pointing at 40, we now say 100 minus 40. What is remaining here is the remaining length. So one of this e.m.f. is given, and the other one is, let's say this one is EX. So EX over that. So you make this the sort of formula, then you find the final value. So this is the equation used to determine the e.m.f. in the cell using the potentiometer method. The next thing I want to look at is the Wheatstone Bridge. The Wheatstone Bridge is simply a bridge. The Wheatstone Bridge is simply a bridge that contains four resistors arranged in a square shape in a circuit. It is a bridge that is used to determine the value of an unknown resistor in a circuit. So let's write. Wheatstone Bridge. If we have something like this, So let's put a resistor here, another one here, then another one here. So this is the plus, the negative, the current will come in here. This is your I from Kirchhoff's law. The current will come in here. This is your R1, this is your R2, this is your R3, this is your R4. This is A, B, C, and D. So another key is connected here with a galvanometer at the center. Good. Now, the current coming in here is I1. The current coming in down here is I2. This is I2, this is your R3. Good. This is it. So there are two keys here. So the circuit is connected. So when the current is passed through, it will flow here. This is I1, this is I2. This is I3, I1, I2. This is I1, I2. Sorry, I1 will flow through here as well. Because this guy and this guy, they are in series. So I1 will flow here and here. So here you have your I2. I2 will flow here. Here I2 also what? I2 will also flow here. This is the direction of flow of the current. And then bust out, then down here. Now, when resistors are in series, they have the same current flow through there. So this and this and this are the same. So this and this are in parallel. So the voltage here is simply V1. The voltage across R1 is V1. And then the voltage across R3 is V3. The voltage across R4 is what? V4. And across R2 is what? V2. Now, I want to choose one of these to be my unknown resistance. Let's call R4 Rx. And then this R2 to be our variable resistor. In such an arrangement, two resistors are standard resistors whose values are known. And then one of the resistors is an unknown resistor whose value is to be determined in the circuit. Good. Now, how is this guy used to determine the value of an unknown resistor? Very simple. This guy is a variable resistor. You are going to vary this value. You connect the circuit and allow the current to flow through it. And vary the value of this variable resistor until you will see no deflection in the galvanometer. That is, the pointer will be pointing at the zero reading of the galvanometer. At that point, we call it the null point or the balance point. Once you reach the balance point, these are the conditions to reach the balance point. For you to reach the balance point, it means that the potential difference BD is the same. So there's no flow of current again. At this point, we say that the potential difference across V, that is VAB, is equal to what? Potential difference across what? VAD. Call this equation 1. Also, the potential difference across what? Across BC is the same as what? That of what? CD. Call this equation number 2. Now, from Ohm's law, from V is equal to IR, it implies that VB is from this point to this point. It means that VB is I1 R1 is equal to VAD. VAD is what? I2 R3. Call this equation what? equation, okay, let's call this equation A, equation B, equation what? 1. Down here, if you proceed, VBC is what? VBC is from here to here. So it means that this is R, let's call this R2. Good. VBC simply means what? I1 R2 is equal to what? VCD is equal to what? I2 RX. We may call this R4 or RX. Let's call it R4. R4. Good. Now, this is equation number 2. Divide equation 1 by equation number 2. So this implies that I1 R1 divided by what? I1 R2 is equal to what? I2 R3 divided by what? I2 R4. This will go, this will go, this will go, this will go. Therefore, R1 over R2 is equal to R3 all over R4. This is the Wheatstone Bridge equation that is used to determine the value of unknown resistance in a circuit. I hope this is well understood. So, any of the unknown resistor can be given. I will say that this R4 can be customized to Rx. That is that for that. We are going to quickly look at the meter bridge. So all of these have their own peculiar equations. So we are going to look at the meter bridge quickly. The meter bridge is simply a practical application of the Wheatstone Bridge. The meter bridge is also used to determine the value of unknown resistance in a circuit. The meter bridge is also used to know the value of the unknown resistance in a circuit. I'll quickly draw the meter bridge quickly. This is how the meter bridge looks like. How is the meter bridge used to determine the value of unknown resistance in a circuit? Very simple. So, a resistor is connected in between this gap. Two resistors are connected between this gap. Two resistors are connected between these gaps. And then, yes, I was correct. Just want to confirm something. Okay. And then your key. Good. So here is the length, as the name implies, the meter bridge. Here is the length of the what? Length of. So the galvanometer is connected here at this point with a big G, and then the jockey. There's a protective resistor here connected. So here is the jockey. Good. So this also works similarly with the principle of the Wheatstone Bridge, as I said. So how is it done? This is your plus, your negative. The current flow here, up here, and then back here again. So this is your R1, this is your R2, and this is your E. So from here to here is a length proportional to what? Is a length proportional to what? We call it L1 to this guy. And from here to here, to this point, is a length proportional to what? R2. Call it what? L2. How does it work? The jockey is shifted on this 100 cm line until a balance point is reached. a balance point where the galvanometer shows no deflection, but the arrow or the pointer points at 0. At that point, you can now, let's say this is the unknown resistance whose value we want to look for. You now say R1 all over L1 will be equal to what? Your Rx all over what? Your L2. So this is how the potentiometer, I mean the meter bridge, is used to determine the value of the non-resistance. Don't forget, this is your key. This is your key. Yeah, this is it. So this is that for that. So in today's video, we are done looking at the meter bridge, the potentiometer, the Wheatstone bridge, the meter bridge, all that the equations are involved in.